Section 2.2 Covariance of two random variables. Recall the properties of the variance. The variance of ax plus b, where a is a constant and b is a constant, will be a square times variance of x. The variance of a constant is 0. If x and y are two independent variables, the variance of ax plus by will be a square times variance of x plus b square times variance of y. What will happen if x and y are not independent? Let us apply the definition of variance for the expression variance of ax plus by. That will be the expected value of ax plus by minus expected value of ax plus by, the whole thing squared. Because the variance of x is the expected value of x minus ex, the whole thing squared. In the variance of x, if we replace it with by ax plus by, you can get this definition. Now let's expand the terms inside the parentheses. We will get the expected value of ax minus eax plus by minus eby. Now take the constants out. We get the expected value of a times x minus ex plus b times y minus eby. Always we have the square outside the whole expression. Now let's expand the square term. So we get the first term squared, the second term squared, plus 2 times the second term. So the expected value of a times a minus ex squared, expected value of by minus eby squared, plus expected value of 2ab times x minus ex times y minus ey. And then taking the expectation outside each of these expressions, we will end up with a square variance of x, b square variance of y plus 2ab expected value of x minus ex, y minus ey. Because the expected value of x minus ex whole thing square is the definition of the variance of x, and the expected value of y minus ey square is the definition of variance of y. Now in the third expression, expected value of x minus ex times y minus ey is named as the covariance of x and y. Hence, in general, the variance of ax plus by is a square variance of x plus b squared variance of y plus 2ab covariance of x and y. Definition 2.2 Covariance of x and y. Let x and y be two random variables with their means ex and ey. Then the covariance of x and y, which is denoted as co-xy or sigma xy, can be defined as the covariance of xy is the expected value of x minus ex times y minus ey. Now distributing the expectation, we get x times y minus x times ey minus ex times y plus ex times ey. This is simply the expand in the multiplication. Then distributing the expected value at the end, you end up with exy minus exey minus ex plus exey. 1 plus exey and minus exey will cancel out. So we end up with exy minus ex times ey, which is the covariance of x and y. here is something you should remember. Covariance measures the dependency between x and y, but its numerical value depends on the units of the measurements of x and y. If covariance of x and y is greater than 0, then x and y have positive linear dependency. If covariance of x and y is less than 0, then x and y have a negative linear dependency. If covariance of x and y is exactly 0, that means there is no linear dependency. We can explain it using this scatter plot. If there is a positive linear relationship, if we draw a scatter plot over x and y, you will see a pattern like the first picture. If you draw a scatter plot when the covariance of x and y is less than 0, you will end up with as the second picture. If we do a scatter plot when x and y has no relationship, the scatter plot will look like where all the dots are scattered everywhere without any pattern, which explains there is no relationship between x and y. The first theorem for this chapter, theorem 2.1. If x and y are independent random variables, then the covariance of x and y equals 0, which means exy minus ex times ey equals 0, which end up with exy equals ex times ey. If x and y are independent, then the covariance of x and y is 0, but the converse is not always true, which means if you end up with the answer for the covariance as 0, that does not mean x and y are independent in general. Let's go back to the example 2.1 and let's find the covariance of x and y. The answers of ex, ey, exy, variance of x and variance of y are as follows. Then the covariance of xy will be e times xy minus ex ey. By substituting the found values, you will end up with the covariance of xy to be 1 over 40. We can see that x and y are not independent. There is a positive dependency between x and y because the covariance of xy is a positive value. If we want to find the variance of x plus y, that will be variance of x plus variance of y plus 2ab covariance of xy, where a and b are simply 1 in this case. We have 3 over 80 for variance of x, 1 over 20 for variance of y, and the covariance of x and y, we found it 1 over 40, 2 times 1 times 1, which is simply 2. So the answer will be 11 over 80. Here is another example. Suppose x and y are two continuous random variables with the given joint PDF. Let's find the covariance of x and y. To do that, first let's find ex and ey, where we get the answer 1 and 2 over 3, and the expected value of xy, where the answer is 2 over 3. Now apply it for the formula of covariance of x and y, which is exy minus ex times ey, that is 2 over 3 minus 1 times 2 over 3, where we end up with 0. But we cannot say that x and y are independent from this result. Unfortunately, it is difficult to employ the covariance as an absolute measure of dependency between two variables. The reason is that the covariance depends on the units of measurements of x and y. For example, suppose x is weight and y is height. If the weight is measured in kilograms and y is measured in meters, and if we calculate the covariance, you will end up with a certain answer. But if for the same data set, the weight x is converted into pounds and the height y is converted into inches and calculate the covariance, you will end up with a different answer. So, for the same data set, when the units of measurements are changed, the covariance value will be changed. To overcome this issue, the standardized covariance is introduced, which is called the correlation coefficient of x and y, which is denoted as rho xy. Let's talk about the correlation coefficient in the third section.